Hi all. In class 19 we are discussing the fundamentals of radical chemistry, and in this first video I'll show you how to make a radical, a general way to make a radical, and talk about what stabilizes radicals and ultimately how to draw these types of molecular orbital diagrams. A radical is an atom or an atom in a molecule that has an unpaired electron, and let me show you one way to make a carbon radical via what's called hydrogen abstraction. In the videos for class 19, I'll be giving also bond dissociation energies because those are going to be important to try to predict which bonds will be broken and made. And for instance, in this hydrogen abstraction, which is the removal of a hydrogen, I'm going to say that this bond right here, I'll point to this one right here, it has a BDE of 435 kilojoules per mole. I have this propane going to react with this bromine radical, and the bromine radical can be indicated with a Br with one dot, or you could draw also the three lone pairs that it already has. You want to realize that this bromine is neutral, and we'll get to formal charges a bit later. What I'm more concerned about now is what are the mechanism arrows to draw this hydrogen abstraction. And what I like to say is that we're going to remove this hydrogen, by the way, this one down here, which has a bond dissociation energy of 435. You're going to start from the middle of the bond, and you're going to take one of its electrons. So if you take one of its electrons from the bond, you're not using a full arrow, you're using a barbed arrow, or many people just call this a fishhook arrow. And I like to say that you meet in space. So those two electrons are going to form a bond between the hydrogen and bromine, but we have a second electron of this sigma bond, and that goes directly onto the carbon. And when you draw the result, you should have a radical at this carbon, and that bromine bonded with hydrogen to make HBr. So there's your carbon radical, and the carbon radical also is neutral. If you remember our formal charge equation, the normal valence electrons of an atom, so this is carbon, so that's 4. Formal charge equals 4 minus, and then I like to say, today's the actually opening day for baseball, 2022. So I like to say sticks plus balls. So you got to remember there's still one other hydrogen here, so it's a carbon with 3 bonds. So that's 3 sticks plus 1 ball, and you notice that this is neutral. If you want to do the same idea for bromine, and that also is 0. We will do more with mechanisms later. For this video, I want to discuss the stability. And before we discuss the stability of radicals, let me remind you that you know the stability of carbocations because they follow the same trends. When you learn about carbocation stability, you'll learn that the more substitution you have on the carbon that has the plus charge, or the more alkyl groups that carbon has, the more stable it is. And here I have the trend written out. It is methyl carbocation, and then we have here primary, secondary, and tertiary. Now there are other types of carbocations, as you know. Allylic. So allylic, let's say we have an allylic secondary. That would be tied with a normal tertiary. So this is an allylic and secondary allylic carbocation. Just like using that analogy, a primary allylic will have similar stabilities with a plain secondary carbocation, and I could draw that up here as well, something like that. So one way you could remember that the more alkyl groups you have on the carbocation, the more stable it is to recall that alkyl groups are indeed electron donating, and as you're donating electron density towards that plus charge, you are mitigating it or you're lessening it. Or you can think of it as being delocalized, where that plus charge is being spread out to the alkyl groups surrounding it. The other phrase you may want to memorize is that alkyl groups stabilize carbocations by what's called hyperconjugation. And I got to the MO diagram a little bit sooner than I wanted, but let me draw you a diagram or a cartoon of hyperconjugation. We know that the carbon that has a plus charge is sp2 hybridized, trigonoplanar, whereas the carbon with 4 single bonds, as you know, is tetrahedral or sp3 hybridized. Here I've represented the carbocation with just the empty p orbital with a plus charge, and due to the proximity of this sigma bond, we do get some sharing of the sigma electrons with this p orbital. There's some overlap, and we can indicate the overlap maybe with an arrow like that. Technically, hyperconjugation is the sharing of electrons between the sigma bond of the carbon hydrogen of the sp3 atom with the p orbital, in this case the 2p orbital of the carbon. So what I have is the sigma CH bond right here donating electron density into the empty 2p orbital of the carbon, and we could put this on a molecular orbital diagram to visualize the energy levels. So a couple of things about these molecular orbital diagrams is that you want to understand that what we're doing is we're combining atomic orbitals, in this case 2 atomic orbitals, to create new MOs, to create new molecular orbitals. And I'm not going to explain too much why we chose these 2 levels, but the p orbital of the carbon is a little bit higher, and we're going to label this the C 2p atomic orbital, right? And then what's lower, probably because the electrons are held closer to the nucleus, is the sigma CH bond, and we're going to label this one the sigma. And you know that bond is made via a combination of the overlap between this hydrogen s orbital and this carbon sp3 orbital, and we're going to consider that area as the sigma atomic orbital. So when we combine these 2 atomic orbitals to make 2 MOs, one will be higher and one will be lower, and you want to keep it symmetric, and these distances, right, this distance and this distance should be the same. One will be bonding and then one will be anti-bonding. Why don't we populate each of these atomic orbitals first, and I'll just use blue. And so this one's empty, and then the sigma has 2, and we'll draw them like that. And then you populate your MOs, and you notice that yes, we get both electrons in a bonding MO. We will call this the pi bonding MO, and simply call it pi. And this is the pi star anti-bonding. So this is a decent foundation. The more alkyl groups you have, right, the more instances of hyperconjugation. So actually you have hyperconjugation between this p orbital and these 3 sigma bonds. We're going to see the same effect for radicals. So here I have set up 3 templates, and we're always going to use the orbital for the carbon 2p orbital, and that's why I want to make all of these equal levels. And then we have here, this is representing the sigma of the CH bond, and in all cases we're going to do carbocation radical, and actually I have a third one here for carbanion, that also is going to be in the same level. Again, this represents the sigma CH orbital. What I would like you to do is, if you can pause the video and draw something very analogous, we'll go ahead and fill in this MO based on what we did on the previous page, and also draw the cartoons for the radical. Right, the radical would have an unpaired electron in here, and also for the carbanion. And then we'll talk about stability between those three situations: carbocation, radical, and carbanion. So here I have the atomic orbital cartoons for a carbocation. Let me label this actually. I've labeled these carbocation, radical, and carbanion, and we're going to see the effect of alkyl groups based on the cartoons and also on the MO diagrams. So practice drawing the cartoons and labeling the atomic orbitals that are being used. You notice that here that the radical, we have an unpaired electron in the carbon 2p orbital, and here for the carbanion, right, we have a lone pair on the carbon, and now we have a filled carbon 2p. Now, if we look at the carbocation, let us just generalize the stability, and this is great stabilization because when we consider the combination of these two atomic orbitals, you get an MO that's lower in energy. So this one, the two electrons dropped in energy, and we'll consider this great stabilization. Now when we take a look at the radical situation, we still get a drop in the energy of these two electrons, but now we have an electron in the antibonding orbital. Overall, though, this is still stabilizing, so we'll give this a good stabilization. And then for the carbanion, now we doubly filled the antibonding orbital, and we would say that I would say no stabilization from the alkyl groups. It turns out that alkyl groups stabilize carbocations about 5 to 10 times better than it stabilizes a radical. But just know that alkyl groups still have a stabilizing effect on radicals due to this drop in energy for these two electrons in the MOs. Since we're talking about MOs, you may remember they have special names when you think about reactivity. For instance, this would be the HOMO, the highest occupied molecular orbital for this carbocation, and this would be the LUMO, the lowest unoccupied molecular orbital. We do have a HOMO for the radical, but here this is not fully filled, but it's not empty. This has a special name. This is called the SOMO, the singly occupied molecular orbital. So I'm asking my students to be able to reproduce the orbital cartoon, the MO diagram, and to explain certain features of the MO diagram, and to understand why alkyl groups do stabilize radicals, but the stabilization is not as much as alkyl groups stabilizing carbocations. Now the last thing I want to talk about before moving on to one more example of these carbon radicals and MO diagrams is bond order. Remember that bond order is the number of electrons in the bonding MO minus the number of electrons in the antibonding MO. So for instance, for the carbocation example, we have 2 minus 0, and the bond order, we have to divide it by 2. I forgot about that. And that equals 1. So it has a bonding order of 1. For the radical, it has a bond order of what? 2 minus 1 divided by 2. That equals 1/2. And you notice that the bond order for the carbanion will be 2 minus 2 divided by 2, and that equals 0. So here I have drawn the same radical that we had before, and we could practice filling in the MO diagram. And we get some stabilization because we have a lower energy level for these 2 electrons. The molecule I want to compare this to is when you have the radical next to an oxygen. And via the MO diagram, we're going to show that it's even more stabilized than just having a plain alkyl group next door. Now, we still have the p orbital with its one unpaired electron, and the only difference here is that instead of a hyperconjugation with the sigma bond, we have a sharing of electrons via the sp3 atomic orbital, right, and the p orbital over here. So again, you do want to realize that these are going to be considered atomic orbitals. And in the middle, we have the same number of molecular orbitals. Some of this is going to be memorization. I do have, purposefully, that this oxygen sp3 orbital is a little bit higher in energy than your sigma CH. And we have these 2 electrons here. I'm not going to go into why that's the case. Just understand or just memorize the starting points. We have this radical here, and that's the same energy level as the original carbon 2p. And what we get here is a massive drop, maybe not massive, but lower than the sharing of the sigma bond, sigma electrons with the 2p orbital. We get a further drop for this MO, and a higher rise for this antibonding. But overall, we have a stabilization due to this drop right here, which is larger than this drop over here. As you recall, when we have carbocations, that oxygen next to a carbocation can stabilize the plus charge a lot better due to resonance, and we have this very good delocalization of the plus charge. I wouldn't draw the resonance for this radical, but it does go to show that there's more overlap and there's more stabilizing effect, even though we're not drawing formally the resonance for this. The bottom line is that this oxygen, right, this sp3 hybridized oxygen with its 2 lone pairs is this better stabilizer of radicals than hyperconjugation, the same effect that we see with carbocations.